Welcome to this presentation. You are watching Vlsi design lecture series. Today we are going to speak about the sequential circuit design and timing issues. In sequential logic circuits, the output not only depends on the current values of the input but also depends on the preceding input values. Here we can see a block diagram of a sequential circuit in which all registers are under control of single global clock. So the next state is determined based on the current state and the current inputs and is fed to the inputs of registers. Here are some of the differences on the comparison between the latches and the registers. A latch is an essential component in the construction of edge-triggered register. It is a level-sensitive circuit that passes the D input to the Q output when the clock signal is high. This latch is said to be in transparent mode. When the clock is low, the input is sampled on the falling edge of the clock and it is held stable at the output of the entire phase, and the latch is in the hold mode. The inputs must be stable for a short period around the falling edge of the clock to meet setup and hold requirements. A latch operating under these conditions is a positive latch. Similarly, a negative latch passes the D input to the Q output when the clock signal is low. Positive and negative latches are also called transparent high and transparent low respectively. Contrary to level-sensitive latches, edge-triggered registers only sample the input on a clock transition, that is either from 0 to 1 for a positive edge-triggered register and 1 to 0 for a negative edge-triggered register. They are typically built to use the latches primitives, and often recurring configuration is the master-slave structure that cascades a positive and negative latch. Registers can also be constructed by using one-shot generators of the clock signal or by using other specialized structures. Static memories use positive feedback to create a bistable circuit. And that circuit having two stable states that represents 0 and 1. Here you can see the basic inverters, that is two cascaded inverters, where the two inverters connected in cascade along with the voltage transfer characteristics of such a typical circuit. Okay. So the VTC of the first inverter, that is V01 versus VI1, and the second inverter V02 versus V01. The latter plot is rotated to accentuate that Vi2 is equal to VO1. Assume that the output of the second inverter VO2 is connected to the input of the first VI1 as shown by the dotted lines here. The resulting circuit has only three possible operations point, that is A, B and C, which are shown in this graph. Okay. And as demonstrated on the combined VTC, it is very easy to prove the validity of the following important conjecture, that when the gain of the inverter in the transient region is larger than 1, A and B are the only stable operating points and C is the metastable operating point. Suppose that the cross-coupled inverter pair is biased at point C. A small deviation from this bias point, possibly caused by noise, is amplified and regenerated around the circuit loop. This is a result of the gain around the loop being larger than 1, and a small deviation delta is now applied to VI1, and this deviation is amplified by the gain of the inverter. The enlarged divergence is applied to the second inverter and amplified once more. So the bias point moves away from C until one of the operating points A or B is reached. So in conclusion, C is an unstable operating point. Every deviation causes the operating point to run away from its original bias. The chance is indeed very small that the cross-coupled inverter pair is biased at C and stays there. Operation points with this property are termed metastable. On the other hand, A and B are stable operating point. In these points, the loop gain is much smaller than unity. Even a rather large deviation from the operating point reduces the size and disappears. Hence, the cross-coupling of two inverters results in bistable state, that is a circuit with the two stable states each corresponding to a logic state. The circuit serves as a memory storing either 1 or 0. In order to change the stored value, we must be able to bring the circuit from state A to B and vice versa. Since the precondition for stability is that the loop gain G is smaller than unity, we can achieve this by making A or B temporarily unstable by increasing G to a value larger than 1. And this is generally done by applying a trigger pulse at Vi1 or Vi2. For example, assume that the system is in position A, that is Vi1 is equal to 0 and Vi2 is equal to 1. Forcing Vi1 to 1 causes both inverters to be on simultaneously for a short time and the loop gain G to be larger than 1. The positive feedback regenerates the effect of trigger pulse and the circuit moves to other state, that is B. Okay. In summary, the bistable circuit has two stable states. In absence of any triggering, the circuit remains in single state and hence remembers the value. Trigger pulse must be applied to change the state of the circuit. Now let us move on to SR flip-flops. The cross-coupled inverter pair, which is shown in the previous sections, provides an approach to store the binary value in a stable way. However, an extra circuitry must be added to enable the control of the memory states. The simplest incarnation accomplishing this is well known SR or set or SR flip-flop. The circuit is similar to cross-coupled inverter pair with NOR gates replacing the inverter. The second input of the NOR gate is connected to the trigger inputs that makes it possible to force the output Q and Q bar to a given state. And these outputs are complementary except for the state SR is equal to 1, 1. This is shown in this figure, which shows the schematic diagram and logic symbol and the truth table. So the state 1, 1 is forbidden here. One possible realization of clocked SR flip-flop is shown, and it consists of a cross-coupled inverter pair plus 4 extra transistors to drive the flip-flop from one state to another and to provide the clocked operation. So this diagram shows the CMOS clocked SR flip-flop. And now let us see about the multiplexer based latches. The most robust and common technique to build a latch involves the use of transmission gate multiplexers. So this positive and negative static latches based on multiplexers can be easily constructed, and for a negative latch, the input 0 of the multiplexer is selected when the clock is low and the D input is passed to the output. When the clock signal is high, that is shown in this figure. So, when the clock signal is high, input 1 of the multiplexer, which connects to the output of the latch, is selected. Okay, the feedback ensures the stable output as long as the clock is high. Similarly, in the positive latch, the D input is selected when the clock signal is high and the output is held when the clock signal is low. The transistor level implementation of a positive latch based on multiplexers is shown, and this circuit diagram you can see. So when clock is high, the bottom transmission gate is on and the latch is transparent, that is the D input is copied to the Q output. During this phase, the feedback loop is open, and since the top transmission gate is off. Sizing the transistors therefore is not critical for realizing correct functionality. The number of transistors that the clock drives is an important metric from a power perspective because the clock has an activity factor of 1. And this particular latch implementation is not very efficient from this perspective. It presents a load for 4 transistors to the clock signal. It is possible to reduce the clock load to 2 transistors by implementing multiplexers that uses only NMOS transistors, which can be seen in this diagram. So, and when clock is high, the latch samples the D input, while a low clock signal enables the feedback loop and puts the latch in the hold mode. While attractive for its simplicity, the use of NMOS only pass transistors result in passing the degraded high voltage of VDD minus VTN to the input of the first inverter, and this impacts both noise margin and the switching performance, especially in the case of low values of VDD and high values of VTN. It also causes static power dissipation in the first inverter because the maximum input voltage to the inverter equals VDD minus VTN, and for the PMOS device of the inverter is never fully turned off. Now let us focus on master slave edge triggered register. The most common approach for constructing an edge triggered register is to use a master slave configuration. The register consists of a cascading negative latch with a positive latch. On the low phase of the clock, the master stage is transparent and the D input is passed to the master stage output QM. So this diagram shows the example of the positive edge triggered register based on a master slave configuration. On the low phase of the clock, the master stage is transparent, the D input is passed to the master stage output, and during this period, the slave stage is in the hold mode, keeping its previous value by using feedback. On the rising edge of the clock, the master stage stops sampling the input and slave stage starts sampling. During the high phase of the clock, the slave stage samples of the output of the master stage, while the master stage remains in a hold mode. Since QM is constant, during the high phase of the clock, the output Q makes only one transition per cycle. The value of the Q is the value of the D right before the rising edge of the clock, achieving the positive edge triggered effect. A negative edge triggered register can be constructed by using the same principle by simply switching the order of the positive and negative latches. A complete transistor level implementation of the master slave registers can be derived in this diagram. So the multiplexer is implemented by using transmission gates, and when the clock is low, the clock bar will be equal to 1 and T1 is on and T2 is off, and the D input is sampled onto the node QM. So during this period, T3 and T4 are on respectively, and the cross coupled inverters hold the state of the slave latch. When the clock goes high, the master stage stops sampling the input and goes into the hold mode. So T1 is off and T2 is on, and the cross coupled inverters I2 and I3 hold the state of the QM. Also T3 is on and T4 is off, and QM is copied to the output. And registers are characterized by three important timing parameters. One is setup time, hold time, and propagation delay. So it is important to understand the factors that affect these timings parameters and develop the intuition to manually estimate them. Assume the propagation delay of each inverter is TPD inverter and the propagation delay of transmission gate is TPD transmission. Also assume that the contamination delay is 0 and that the inverter deriving the clock bar from clock has a delay of 0 as well. And the setup time is the time before the rising edge of the clock that the input D must be valid. This is similar to asking the question, how long before the rising edge of the clock must the D input be stable such that the QM samples the value reliably. So for the transmission gate multiplexer based register, the input D has to propagate through I1, T1, I3 and I2 before rising edge of the clock. So this ensures that the node voltages through I1, T1, I3 and I2 and on both terminals of the transmission gate T2 are at the same time. Otherwise, it is possible for the cross-coupled pair I2 and I3 to settle to an incorrect value. The setup time is therefore equal to 3 into TPD inverter plus 3 TPD TX. The propagation delay is the time that it takes for the value of QM to propagate to the output Q. You can notice that since we included the delay of I2 in the setup time, the output I4 is valid before the rising edge of the clock. Therefore, the delay TCQ is simply the delay through T3 and I6, that is TCQ is equal to TPD TX plus TPD inverter. And the whole time represents the time that the input must be held stable after the rising edge of the clock, and in this case the transmission gate T1 turns off when the clock goes high. Since both D input and clock passes through the inverters before reaching T1, any changes in the input after the clock goes high do not affect the output. Therefore, the whole time is 0. Thank you.